Hello everyone. Oh, yeah, it's good. So I'm Elliot Lumet, and I'm working in the EXPLEARTH share in CNRM Météo France under the supervision of Laure Reynaud, and I'm working on diffusion downscaling for regional weather prediction. So, okay, it's not a problem for this slide actually. So to give you a little bit of context in Météo France to inform this its forecast, Météo France develops and operates two models. So ARPEGE, the global one that is operating on a 25 to 10 kilometers resolution, and a regional limited area model, AROM, that is operating in a resolution between 2.5 and 1.3 kilometers. And the objectives of my postdoc, are to develop a statistical downscaling model to learn the relationship between these two models. And to do so, we aim to leverage a diffusion model to avoid the standard issue with the models that are based on RMSE loss, because these models are known to blur the fine scale features. Or the reason we are using regional models is to recover the fine scale features to provide better forecast for local phenomena. So in terms of approach for our first demonstrators, we trained it on 5 years of hourly AROM and ARPEGE forecast from the operational chain in Météo France. And we are training to learn simultaneously 30 variables that are discretized over about 500,000 grid points. And we use the EDM diffusion algorithm from Karas et al., working on the residuals. This means the difference between the low resolution and high resolution fields. And to do so, we train graph transformers that operate over this kind of standard encoder, processor, decoder architecture. The only specific thing is that we have two different encoders, one that gets input from the low resolution in grid here, and one that has inputs at the high resolution that are forcing, such as the orography or the presence of the sea or not. And here you have a result example with the 2-meter relative humidity for one date in the test set, which is actually zoomed over the southeast of France. You have the Mediterranean Sea. On the top, you have the ARPEGE low resolution input. So you can see that it's blurred because it has less resolution. And at the bottom, you have 3 different snapshots. So 2 are the diffusion model, because the diffusion model is probabilistic. So you can sample it to obtain different results. And one is the truth. So I can let you guess who is who, but it's kind of difficult. So here are the results. So the truth is on the middle. And you can see that it's a bit confusing because the 2 diffusion samples are actually quite different. This means that the model is able to generate some spread in this forecast. But in the meantime, we have one sample that is very close to the truth. So yeah, to conclude, our model is able for the surface variables to learn the fine scale features related to the orography, and also to provide ensembles that might be relevant for uncertainty quantification. So for the perspective, we are actually pushing the evaluation because we have a lot of work to do to evaluate versus AROMI first, but then against observations to know if it can be at the same level of AROM on operational conditions. And we are also working on this ensemble thing to know if we can use it for uncertainty quantification. And then we would like to compare it, so this downscaling approach with the autoregressive emulator that is actually being developed at Météo France. And finally, we would like to work on noise because we see that with our different variables in the meteorological problem, we have issue with the spectra of these variables that are different and that are not being destroyed at the same pace with the white noise of the diffusion. So, yeah. Thank you.